Okay, we're moving on in section 3.3. We're getting near the end of the section. We have a couple of observations to make and a couple of examples to work. The first thing I want to tell you is that a polynomial of degree n can have at most n distinct zeros. And so let's think about the previous example from the previous video. We had f of x equals 2x to the fourth minus x cubed and so on. And we found the zeros, and there were 4 of them. And notice that this polynomial is degree 4, right? The degree is the highest power on the variable. So a degree 4 polynomial with 4 distinct zeros. Here they are. We showed all the work to find these zeros in the previous video. It should seem reasonable that if you have a 4th degree polynomial, then 4 is the most number of zeros you could have, right? Because if you think about factoring the 4th degree polynomial, you would get down to 4 linear factors, and then each linear factor represents a 0. So let's look at the next example. You have f of x equals x cubed plus 3x squared plus 3x plus 1. Since it has degree 3, you might expect to get 3 distinct zeros, but that's not the case. In fact, you only get 1. Let me show you why. And you know, you could go through the process we learned in the previous video to factor this for yourself. We won't take all that time right now. We'll just go ahead and say that this factors to x plus 1 to the 3rd power. And so there are 3 factors, but they're all the same, x plus 1. And so we say there is 1 distinct zero. It is x equal negative 1. And we also say that this 0 has multiplicity 3. Because it occurs 3 times for the 3 factors that are all the same. So the multiplicity of the 0 means the number of times that the 0 occurs. Let's work some examples. Let's go to example 6. And let's find the zeros and their multiplicities. These problems are a little bit easier than the previous videos. Can you see why? In these examples, the functions are already factored for us. So that's a big help. So we'll list out the zeros and their multiplicities. Maybe the place to start is with the factors, right? So in number 6a, there's a factor 3. We can disregard that. There's a factor x, and we say x equals 0 is a 0, and its multiplicity is 1. And then you have a factor of x minus 2. And so you set that equal to 0 and you get x equals 2. And again, the multiplicity is 1. And then you have a factor x minus 3. And sure enough, the multiplicity is 2 this time. If x minus 3 is the factor, then the 0 is x equals 3 with multiplicity 2. Okay, the next one is about the same. There's one extra wrinkle, if you will. Let's go on and let's have a look at that. So this time we have a factor x plus 1. And so x plus 1 equals 0. gives us x equal -1. What's the multiplicity? If you said 2, you got it right. What's the next 0? The next 0 is 1. It comes from the factor x minus 1, and its multiplicity is 3. The last one is just a little bit tricky. It's x squared minus 7. And so what we're going to do is we're going to have to write out that quadratic factor. So that's not a repeated factor, right? That square doesn't mean that x minus 7 repeats. That square is inside the quadratic factor. We're going to have to solve the quadratic. And so we can add 7 to both sides, and we can use the square root property, and we can get rid of the square on the left by putting a plus or minus root 7 on the right. And so there are 2 more distinct roots. There is a distinct root at square root 7 with multiplicity 1. And there is another distinct root at negative root 7, also with multiplicity 1.